So now that we're aware which one is the alpha and the beta structure of fructose, we can clearly mark them on our own. So in this particular structure on the left side, we can see that this OH is appearing at trans to this CH2OH. So we can clearly name this particular cyclic structure as the beta form. And on the right side over here, we have CH2OH appearing at cis position with this OH group. So we can call this as the alpha form. Okay, so this was a differentiating factor that we talked about. Now, let us just decide on the configuration whether the fructose is a D or an L configuration carbohydrate. So here we have fructose at this bottom side, and we can clearly see which chiral carbon allows us to see whether the fructose will have a D or an L configuration. It is the last chiral carbon. So this last chiral carbon, we notice that this OH is actually lying on the right hand side, and therefore, since it lies on the right hand side, we can clearly see that the fructose can be called a D fructose. Okay, so since the configuration of OH is on the right at the last chiral carbon, we call it D fructose. So this beta and this alpha can be accompanied by a D. Okay, so both of them will be accompanied by a D. Now, for the rest of the name, let us see and take a hint from this particular five-membered ring that we have at the right-hand corner. So this particular five-membered ring over here, it's called as furan. Now, our furan over here looks a little similar to the cyclic structures of fructose that we have drawn. So this furan will help us in naming these two structures. And how does it do so? The beta D, we can call it fructo, and then we can put the name furan, and I call it fructofuranose. Similarly, the alpha one will be called alpha D fructofuranose. So this furan over here is helping us in a better naming of the alpha and the beta form respectively. Now, we discussed that in the beta form, this OH and the CH2OH are lying at trans position, and in alpha they are lying at the cis position. So we know for a fact that this beta D fructose, where the placement is at trans, is of course more stable than the alpha form, because if these two OH and the CH2OH group lie on the same side as is in alpha form, then this particular cyclic structure become less stable. The placement of two big groups gonna go cause a lot of steric hindrance. So we can say, if we are to discuss the stability order, that what can we say, that this particular beta form is greater stabilized than the alpha form. So this is a conclusion that we can easily draw out looking at the cis and the trans form. Now, what else can we see in these two particular cyclic form is that they are only differing from each other because of the placement of the CH2OH and this OH at the carbon 1. Okay, so if I look at the carbon 1 of both the cyclic structure, we notice that the only point of difference between these two is that the placement of OH on this carbon 1 is at the top and here is at the bottom. Similarly, the CH2OH group lies at the bottom here and it lies at the top. The rest of the structure is completely similar and they are resembling each other in the rest of the carbons. Okay, so what can we say, that they are only differing in configuration at the C1 carbon. And we know that if there is a difference of configuration while the rest of the molecule looks similar, we can call them diastereomers. So we proceed and say that these two are diastereomers of each other. So alpha and beta are diastereomers. Now, this was a point of difference. Now, since they are diastereomers, we learned about a subcategory within the diastereomers where we saw if there was only one carbon which was differing in configuration, we could call them as epimers. Okay, so this beta and this alpha are also epimers. So they are diastereomers and epimers. Also, we saw in glucose that if these epimers were in a cyclic ring, they were called anomers. So, our alpha and beta are also anomers. Now, we have decided that they are diastereomers, they are epimers, and now they are anomers too. Anomers, just right over here, that anomers are nothing but cyclic epimers. And since we can now place out an anomeric carbon which makes us differ from these two structures from each other is this particular carbon, that is the C1 carbon over here, as well as over here the C1 carbon, and therefore this C1 carbon can be called as the anomeric carbon. So let us write here the new fact that we just discovered is that the C1 carbon is the anomeric carbon. Okay, so we have decided on some facts about all of them, and here we have seen all of them. So we have decided that these two are anomers and we have got the anomeric carbon also. So can we now call them as two anomers? These are nothing but anomers of each other. This anomer term covers epimer also. It covers diastereomers also. So now we can call these two structures as anomers of each other. Also, since we have got alpha and the beta form, and we noticed in glucose that the alpha and the beta form were existing in an equilibrium with each other, and when they were doing so, mutarotation was also occurring. So this alpha and this beta form are actually in equilibrium with each other, and therefore in fructose also mutarotation occurs. So we can just write here only that mutarotation exists here also. Okay, so a lot of point of commonality between our fructose and our glucose. So we can see that mutarotation exists here. And what was mutarotation? Mutarotation was when the specific angle of rotation changes with time till equilibrium is attained. So till the alpha form will be existing in some degrees, we'll have an angle of specific angle of rotation, and that degrees will try and approach our equilibrium specific angle, and the beta also will try to move forwards towards the equilibrium specific angle or the effective angle. So both of them are actually in equilibrium with each other, and their angle of rotation will keep on changing with time till equilibrium is attained. So we can say that mutarotation exists here in fructose also. So we have highlighted a lot of points in this particular from the alpha and the beta form. So the main point here that we were discussing was beta D fructofuranose and alpha D fructofuranose. And in this, we have seen that they are anomers of each other. They are also epimers. And since they are cyclic epimers, they were called anomers. And we have also established the fact that the C1 carbon here was the anomeric carbon. So here we are seeing all the properties that occur in cyclic fructose.